Uh, Thanks to Jingwu, we have an excellent overview of progress on pre-processing for both marine and onshore. So the state that we're at is the reference wave has been removed, ghosts have been removed, and now we're with primaries and multiples, or meaning all of the events after a ghost removal have at the receiver the wave starts down, and I mean at the source the wave starts down, and at the receiver the wave is moving up, yes? And then, as we said earlier this morning, given deghosted data and reference wave removal, it's at that point that we define primaries and multiples, yes? And so primaries being with an event that has one upward reflection and a multiple having two or more, and then the multiple again defined by the location of the downward reflection. If there's one reflection at the free surface, one at the free surface, it's a free surface multiple, no matter what the rest of the history is. If it hits that free surface once, it can ring around, it's a free surface multiple. To be an internal multiple, all the downward reflections have to be below the free surface. Okay, so so we're into, thanks to Jingwu, we're into the business of primaries and multiples, and the question is, why are we taking multiples out? Yes, before we go to how we take them out, we're going to say why. So I'm going to. There's a talk tomorrow where there's a comparison in detail of different migration methods, in particular RTM with what we call Stolz C3, yes? I'm not going to do that now. Now I'm going to ask your indulgence to assume that the third of the imaging principles that Claerbout describes, and we'll go through them in a minute, is superior in terms of interpretability, in terms of processing, okay, in terms of not being a high frequency approximation and resolution differences. So why we're going to focus on that best defined imaging principle among the three that Claerbout mentions, as and to look at the role of primaries and multiples in migration. Look at the most well-defined migration method, yes, and then examine. So the purpose of this next talk is that. Find a migration method. First of all, the migration method has got to be able to deal with reflectors in the medium, because if it doesn't have reflectors, why should that data that has primaries and multiples, where the multiples come from? Yes, if you're going to have a prediction of a source and receiver at depth, and you're assuming your data is primaries and multiples, you have to have a medium that can generate multiples. Yes, so you can't have a smooth medium and assume you've predicted the source and receiver at depth correctly, yes? So what happens in practice when you assume a smooth medium and you have primaries and multiples and you do source-receiver coincidence at time equals 0, guess what happens? You don't have that experiment. You get multiples being artifacts, yes? You understand? You don't get a local image. But that's racing ahead. So I'm going to go quickly through this, and then there's going to be a second tutorial on the inverse scattering series. If I can achieve one goal there, that you can see what is the logic behind the following fact. The inverse scattering series allows for isolated task subseries to achieve any processing goal you can imagine directly and without subsurface information. Okay? There's one slide. If you can follow the logic on that one slide, the math, that's it. Okay? It's okay. So that's the second tutorial. So I'm going to go quickly through this. So what this says is, if you want to know what the role of primaries and multiples are in seismic processing, how do we find structure and how do we do amplitude analysis, is from migration and migration inversion. The original purpose of migration was to map an event in time to where on a reflector that event, in other words, you have an event on time. In time, you want to know what point on a reflector was there a reflection that caused that reflection in time. That's it. So if you think of that, how are you migrating a multiple? A multiple doesn't have a reflection point. It has reflection points, okay? Points. So the whole thought of this is not valid, okay, for multiples. And so if you're migrating a multiple, are you migrating to every point that it's reflected? That thought makes no sense. In addition, the most sophisticated method for migration is what we call Claerbout 3. Well, let me get some language here. What's this Claerbout 1, 2, 3? In other words, methods that use wave theory for migration have two components. The activity they use for wave theory for migration had its golden age in the 1970s. John Claerbout, Bob Stolt, Schneider, French, people of that time. 1978 February, Geophysics, 2 landmark papers in 1 issue of Geophysics. Stolt migration and Schneider integral formulation. Amazing period of productivity. So in each of these, there is a imaging condition and there's a wave propagation component. There, John Claerbout in 1971 in a paper lists 3. He doesn't claim that he invented them, but they're in his paper, so we refer to them as Claerbout 1, 2, 3. In fact, so the first imaging principle is what's called the exploding reflector model. That principle is for stacked data, okay? Zero offset data. And it says basically if you had a source and receiver coincident and you did some kind of ray theory that back and forth there's a symmetry, time to the reflector, time back. And so if you had the time that the reflection arrived back, and I go with half the speed that we imagine the wave is traveling to time 0, I'll get the reflector, yes? In other words, this will be, yes? If I did the full time and actual speed, I'll find the source. If I want the reflector, yes, I'll go with half the time, half the speed, yes, half the speed to time 0, I get the reflector. So the idea was, in that view, at time equals 0, the reflector exploded and sent this wave with C0 over 2 to the receiver. You understand? That's the exploding reflector. That thought is for zero offset data. We're not going to discuss that. The 2 other principles are for unstacked data. The second is time and space coincidence of up and down going waves. The idea there was you take the reflection data back and you take the source field forward until their time and space coincidence. You don't take the source forward, you take the source field forward. And where that source field forward and the data back are time and space coincidence is the location of a reflector. That we call Claerbout 2 imaging. That is the basis of RTM. Okay? RTM evolved from that in the original time of 1971. This was considered take the data back in space. Space, right? One-way wave back. This evolved imaging condition 2 in 1980s. Whitmore, McMecken, yes? Instead of going back in space, go back in time to get a diving wave, yes? So you're going back in space and going back in time are the same if you have one-way wave, yes? If you have two-way wave, yes? Then you can get overhang, yes? the overthrust belt, amigo. So that's imaging condition 2. The key point about imaging condition 2 is the source field is going forward, not the source. The reflection data back, the source field is propagated forward, and you look at time-space coincidence. Claerbout 3 is a different principle. It says predict what a receiver and a source would do at depth, not the source field. What would a source that's in the Earth and a receiver in the Earth do? Make them coincident, yes? And in other words, if you have a source and receiver in the Earth, and I ask for all time, it will give me information about the whole world. If I ask for small time, Claerbout said, yes, then you will get something proximal. It only has small time. It has to have information in the neighborhood. That was a brilliant thought, yes? And that's a major contribution. So 2 and 3 are different, and the major difference is what happens to the source. In one case, the source is being predicted down. In the other, the source stays, and its field is going forward, yes? That makes all the difference in the world. Without telling you all the superior qualities of 3 to 2, yes? I mentioned that 2 not only evolved by going back in time instead of space by the people I mentioned, it also further, it became an amplitude, a geometric optics reflection coefficient by the people I mentioned earlier, Norm Bleistein, Sheng Zhu, Yu Chang, yes? These people made a geometric optics contribution beyond just back in time. So 2 evolved. 3 evolved basically due to Stolt. Stolt and Clayton, Stolt and myself extended that zero offset concept. The zero offset, if you do zero offset at time equals 0, you're going to get a number. You're going to get 7. You tell me what, for source and receiver coincident at time equals 0, what's the value? You get 6, yes, at that point. The power there, the power is you get a yes or no. If you have a source and receiver here at time equals 0, and it's coincident, and you get no answer, you get a 0 value, there is no reflector there, okay? If you get a non-zero value, there's a reflector there. Something is local going on there, okay? That's extremely important, okay? That thought, you'll see when we show you the differences tomorrow, why that's so important. What Stolt did with colleagues is extended 3 to give amplitude information, not just a number, but a function. If I want amplitude information at that image, I need a function of angle, yes? So he relaxed the 0 offset, allowed for non-zero offset at time equals 0, and then introduced a point reflectivity. So please understand, imaging condition 3, Claerbout 3, we call it Stolt C3 because Stolt made major advances beyond the original, can image, if you have a specular, you have a horizontal reflector, it will give you a reflection coefficient, not geometric optics, a plane wave reflection coefficient that you need for amplitude analysis. If you have a curved reflector, there is no plane wave reflection coefficient. You hit that with a plane wave, there's no plane wave that comes out, okay? So Stolt introduced something more general, a point reflectivity, okay? Which is exists there, means if it hits there, it spreads. But, and it knows automatically whether it's specular or diffractive or pinch out, and automatically, without you having to do diffraction imaging, and one formula gives you the structure and amplitude analysis, whether they're specular or none, okay? That extension is only possible in 3. So if you think we're in some kind of campaign against 2, the book that Bob Stolt and I wrote in 2012, 70% of that book is 2, is Claerbout 2, variants on that, yes? I wasn't thrilled with that, but that's the way it was, okay? Volume 2 won't have that orientation, okay? But there's plenty of advance, and so he's doing very much the Yu Zhang, Sheng Zhu, Norm Bleistein kind of advances on Claerbout 2, yes? There's certainly value. So right now, without showing you any justification, yes, there are superior benefits in terms of resolution, in terms of ability to image. This principle 3, is not a high frequency approximation. It turns out that the imaging principle 2, is a high frequency approximation. What do you mean? You give me a source and receiver, one source and one receiver, and do RTM with that, and you'll get a travel time curve. As soon as you see a travel time curve, you're in high frequency land. You're seeing candidates. Ray theory, just like Kirchhoff. Here's one time, here's a source, here's a receiver, here's one time. I put it on an ellipse. That ellipse is high frequency thinking, yes? So RTM is just like Kirchhoff, it's high frequency. So again, all these comments are not, will be justified tomorrow with examples, yes? Now they're just gratuitous. I'm asking you to trust me that we're going to pursue 3 right now for the issue of what is the role of primaries and multiples in migration, yes? So we have this is we're going to predict the source and receiver inside a volume. We're going to assume we know the properties of the medium inside the volume. If you want only structure, all I need is velocity. If you want to do amplitude analysis, if you're interested in migration inversion or some AVO at depth, you need to know everything about that medium. Okay? Of course, you need the real source and receiver experiment. For that, you need to know the medium. Okay? So that's a very high bar. And if you're doing nonlinear processing for amplitude at depth, that's an extremely high bar in information above. We're assuming whatever your objective is for migration, whether it's structure or beyond, you have that information. And if you have the information, there's a surface integral. And G0 has to be a Green's function that satisfies the properties inside the volume, just like the field does, both. But as we said, when we derived this, remember we said, for this Green's theorem business, any G0 will work. Yes? Any G0 will work. We're going to exploit that. So here's a volume. So what is this about? We're interested in a Claerbout 3 image, meaning we want to predict a receiver and a source inside the volume, and then ask them to be coincident, ask for small positive time, and move that experiment around until we get non-zero values. When we get non-zero values, we're at structure at that location. Clear? So I need to be able to make that prediction. Please understand, Green's theorem does not talk about information on a surface. Green's theorem is you give me a surface of information and I predict inside. Okay? It's a closed surface. Okay? Closed surface. A closed surface, you predict inside the volume within that surface. So we break that surface up into upper and lower. We could have it with a cylinder with walls and a lower and a upper. That detail we'll leave alone. Okay, I'm leaving this alone. Okay. What we can show analytically is if the wave you're trying to predict, in other words, let's assume that within this volume, this field called P is moving up. And from surface measurements, I want to predict a field inside that volume that happens to be only moving up. Yes? If that's the case, then you can show that choosing an anti-causal Green's function for predicting a wave that's only moving up will allow only information on the upper surface to be required, because information on the bottom surface will not be called for. If I choose G0 plus, then information on the bottom will be required and not on top. Yes? But since I have information on top and not on the bottom, yes, I choose anti-causal. Yes? For a wave moving up. Yes? For a wave moving up. That thought leads to FK migration. In other words, you get this shift. E to the minus IK, Z minus A, P of A. A is on top, you just shift down. Okay? Detail left. That Green's function up there is. Now, what if your wave that you want to predict is not moving up? That's moving up and down. Why do we need up and down? Because we're talking about multiples, yes? We're talking about predicting a wave inside a medium that generates multiples, yes? Generates primaries and multiples, yes? It has to be able to predict a two-way, at a point inside that volume, it has to be able to predict a field that is not one way. To do that with measurements only on top, you have to pick the Green's function and its normal derivative on the bottom, both to vanish. Okay? We call that G0dn. In other words, in classic math physics, they tell you, if I get the field all around, yes, they call that Dirichlet. Let's talk about the last slide. There's a slide I skipped, maybe most important. Here's a slide. You get P grad G, G grad P. If you give me P and the normal derivative all around, you can pick any G0 you want, and you'll get the field in there. People will say, wait a minute, that's overdetermined. It's not overdetermined if you give me measurements. Measurements are never overdetermined. What's overdetermined is if in your mind you give me some function P, and in your mind you give me a normal derivative from your brain, yes? Then it could be that's just the field alone makes it happen, you understand? But measurements are not going to be overdetermined. People say, you understand? Measurements are consistent with it, okay? So if you give me measurements of P in the normal derivative, it will work for any G0. The question is, what's the least amount that will work, yes? The least amount will work is you give me the field all around, or you give me the normal derivative all around. One is called Dirichlet and one is Neumann, yes? To arrange it, if you give me the field all around, I got to have the other guy go away, so I have to make the Green's function vanish, so that I don't need the normal derivative, yes? Or if you give me the normal derivative, yes, I have to have the normal derivative of the Green's function to vanish, because it's P grad G, G grad P. If you only give me P, the other one's got to go away, yes? So that's what that first story talks about. The bottom story says, for one-way wave, you can pick an anti-causal Green's function, as we said. What does that mean? If you have a wave that's moving up, anti-causal will tell you where it was from where it is. If you make causal, you'll need the information on the bottom, because you said the wave's moving up. So from where it is now, here's the future. Yes, going up. Oh, okay. So the bottom line is to have a two-way wave in this medium predicted. You need a Green's function In other words, I got to get rid of the boundary where I don't have information. So make the Green's function and its normal derivative both to vanish at some level. What do you mean some level? There are people, I'm old enough to remember when I worked at City Service Oil Company in Tulsa, people made fun of John Claerbout. Wave equation, no panacea. I heard. I know now he's a staid, conservative Rock of Gibraltar, but when he started, it was not. Okay, and there were all kinds of statements. Oh, and John Claerbout, if you give him the velocity, he'll give you the reflectors. Oh, thanks for nothing. If you give me the velocity everywhere, what do I need? I'll know everything. That's not what John Claerbout said. John Claerbout said, just give me the velocity to where I don't know something, and then I'll find something. He didn't need the velocity everywhere, just enough to determine some unknown. So that was interesting for me, how not only, of course, Claerbout, but Stoltz and Schneider were all considered radical. Radical, yes, truly. Okay, I won't name names who told me all this, but when I would discuss those people back in the day, I was considered radical. Interesting, how far we've come. So the point here is we don't have information on the bottom. You have two-way propagation. If you want information on top, you have to pick the Green's function and its normal derivative to vanish. And so we arrange that. So that's what, in other words, then you need the field and the derivative on top. You say, well, what if I don't have the derivative? So the answer is, Jingwu just spoke to us. Jingwu just spoke, we're going to deghost. If you deghost, getting the normal derivative is not a problem, because it's one way at the receiver, yes? If it's one-way wave, finding the normal derivative is just IKZ or something, right? If you have a two-way wave, then the normal derivative is a separate measurement. So the field and the derivative is not a big deal here, but this is the integral. This brings the source and receiver down. This is not a new imaging principle, okay? This is John Claerbout, 1971, imaging condition 3 for a heterogeneous media, where I don't want to assume one-way propagation. You could say, well, if it's smooth, what about WKBJ? Why don't I want to do that? Because I don't want any high-frequency approximations. I want to have fidelity of all frequencies at the target. You'll see about that tomorrow. You understand? So we're not, the imaging condition, Claerbout 3, we'll see, is not making a high-frequency approximation, and we don't want any propagation model to be making a high-frequency approximation. Anyway, that's the formula. So this is an example of, this is an example for Dr. Chung Fu, where are you? Here, where that G0DN business imaged this C0, C1. Yes, you do RTM through that one reflector, you get all kinds of issues. And we have Dr. Fachi Liu published paper getting rid of rabbit ears. You get rabbit ears. You do Claerbout 3 through that reflector, image above, put the source receiver above, put the source receiver below, no rabbit ears. You get dark, light and dark. In other words, how do you predict the source and receiver below? Above it, it's two-way propagation to get the receiver under. You need that G0DN. So what we're going to be doing now is we're going to take a simple set of layers, yes, with primaries and multiples in the data, yes, and bring them down, bring the source and receiver down, and see what happens to the primaries and the multiples, yes, where we have the medium. Understood? And we'll see what the role of multiples is. There you go. This is a normal instance case. You follow? There was a source and receiver, and there's only one reflector. Yes? There's no multiples. It just comes down, and that source and receiver, and now it's being going underneath. Yes? What is this? A Claerbout 3 experiment. Yes? A source and receiver being predicted. Okay. Now watch what happens with multiples. This is a free surface multiple. Okay, so watch. You see how this is coming down? You see this free surface multiple? When this is right above here, the primary that was up here becomes a primary like that. And that multiple remains with this time. When you ask for t equals 0, the multiple is not there. You understand? When the source and receiver, can we make this stop at the above? It goes on forever, okay. In other words, when the source and receiver, maybe I'll draw it here. You have your original measurement, yes? You have a reflector here. Here's a primary. Here's a free surface multiple, yes? Now you bring it down. This primary becomes this primary, yes? And this free surface multiple becomes this free surface multiple, yes? Still free surface multiple. When I say small time, there's only one guy with small time. This is at some, it doesn't contribute. What is the lesson here? If you had an accurate discontinuous velocity model, if you had an accurate discontinuous velocity model, then you don't need to get multiples out. They'll never image. Okay? In other words, at every point, the multiple comes in later. The same for internal. Yes? Multiples are an issue for one reason, because we don't have discontinuous velocity. The whole multiple removal business would go away, okay, if we could have accurate discontinuous, because they come in later. You understand? The reason they're an issue is in practice we have smooth. If you have smooth, then you're taking a source and receiver down constantly with a smooth, yes, and you're treating a multiple like it's a primary. So it'll image somewhere, okay? Those false images are the artifacts that we need to remove. The only reason we need to remove multiples from recorded data is we use smooth velocity. If we ever are, we struggle very hard at top salt to try to get a discontinuous. That's the only case, okay? But if you could have an accurate, I'm not saying accurate forever down. I'm saying accurate discontinuous down to where you want. In other words, this, John Claerbout is not saying you need the velocity everywhere. He wants the medium, and then there's unknown. This is never assumed to be known. Known, 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 don't know. Locate this. You understand? If this was all known and discontinuous, this will never, multiple will never cause an issue. Free surface nor internal. Will never image. They'll never contribute to the image. So the reason multiples are an issue today is for smooth velocity, okay? They cause artifacts, yes. And so that's the reason. Okay, so we need primaries. Let's move on. But what if we need primaries? But what if you don't record all the primaries? Let's say you have an insufficient. So for a given velocity model of an unrecorded primary, as we know, there is a significant activity of using a recorded multiple let's say this one, and let's say you had an event like that, the solid line. You had this recorded and this solid line recorded. You can take that solid line and forward propagate it like an R2, a C2, like an RTM. Make its field go forward, yes? And take the multiple, which is on the other end of that dashed line, and make it go back, getting an approximate image of this unrecorded primary. So if this is recorded and the solid line is recorded, you can use the method I just described, and there are many papers by PGS and elsewhere describing this in detail. You use this recorded event, this recorded sub-event of that multiple, to get what is assumed to be an unrecorded primaries approximate image. That approximate image is an approximate RTM image, okay? So what I mentioned earlier is, let's say this is the multiple, for example, that you recorded. And let's say this is, like there, a recorded sub-event that you're going to go forward and take that multiple here and go back. But let's say this happens to be, this unrecorded event happens to be itself an unrecorded multiple, yes? Not a primary. Then this will give you an artifact. You will treat this, go back, go forward, you're going to get an image here that's false. So just as with recorded primaries, we need to remove recorded multiples. To go after unrecorded primaries, you need to go and remove unrecorded multiples. So that's an interesting thought. Someone could say to me, well, how are you going to get rid of unrecorded multiples? I say, why are you asking me? Okay? I'm not trying to do this, but it shows a sort of an interesting consistency. But the main point here is, what are we looking for here? We're looking for an unrecorded primaries image, yes? If this was recorded and this was recorded, you don't need to do this. The only reason this has this idea has value if there's an unrecorded primary as a sub-event of the multiple. You're after primaries, yes? Recorded and unrecorded. So why I'm making this speech is there's nothing adversarial, you understand? We're all after imaging primaries. They're the only things that imaging makes sense for. If you had this as the unrecorded event, you better get rid of it. It's a multiple. You can do your RTM on it. You're going to get a false image, just as if I migrated a recorded multiple. Yes, with a smooth velocity. Okay, so that's so why for us is in this group are we prioritizing removal? We're prioritizing removal because Claerbout 3 and Stoltz extensions has more potential, yes, for structure, imaging a pinch out. RTM in principle can't image a pinch out, yes? You understand? That's a very important imaging point. That's what we're going to be looking at in the future, yes? More complicated structure. And so if you're after maximally deriving benefit from recorded primaries, you got to put a lot of effort at removing recorded multiples. That's the reason. Do we feel people, do we encourage those who are using multiples? Of course. But I'll say something now that won't make all of our friends happy. One problem is permanent. As long as we can't find a discontinuous velocity, we have to remove recorded multiples. Okay? If there's some day that we can find a discontinuous velocity, you don't have to get rid of multiples. Yes? But so if you consider, if I consider that issue of finding a accurate discontinuous velocity not in any near future, in that sense, the removal of multiples is permanent, yes? Permanent. The using of multiples is transient. Why? In the history of seismic processing, there was a time we never did 3D. Everything was one line. I know nobody here remembers that, but there was a time there was no 3D. There was no cross-line data. So we all did asymptotics for cross-line approximates, you know, to 3D source, yes? All kinds of processing methods, yes? Trying to accommodate a world where for data we didn't have. And then what happened? Suddenly we got the data. So when you're looking at dealing with issues of insufficient primaries, my suspicion is primaries will be collected. There will be more collection. And when more primaries are collected, the need for finding uncollected primaries or unrecorded primaries images, the interest in that will get less. Okay? That's just in the interim, as I wrote in a recent paper, in the interim, we need both, remove and use. In the longer term, I think the use will diminish because it's a limited data issue, yes? Okay. Okay, so that's a story about why we need to remove multiples. When we're going to move forward, there's a talk on ISS. Yes?